Swayam Prabha. Digital India. Educated India.
Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We both are from Civil Engineering Department, IIT Kharagpur. We have divided this course into two parts. The first part, Environmental Chemistry, will be covered by me, and the second part, that is environmental microbiology, will be taught by Professor Sudha Goel. Now, in my first module, I discussed about the acids, bases and salts. In the second module, I discussed about the chemical equilibrium. In the third module, I discussed about the chemical kinetics. In the fourth module, I covered the catalysts, and this is my fifth module. And in this module, I am in this lecture number 25, I am covering chlorine chemistry and disinfection part C. In the last two lectures also I discussed about chlorine, how we can disinfect the water with chlorine. I discussed about the chemistry of chlorine and also the chloramine formation, the chlorine demand, breakpoint chlorination curve, etc. And in this lecture I will cover the determination methods. That lecture content of this lecture is shown here. The iodometric method for total chlorine determination, and free chlorine and chloramine determination separately. We have seen that how the chloramines are being formed. We have also seen that we are using chlorine, how much chlorine we are adding, how much chlorine is remaining as residual chlorine, how much is present as free chlorine or residual chlorine. Those things are very important. I have shown you the breakpoint chlorination curve. In the y axis I have shown that residual chlorine we have plotted. So, how to know this? That is the question today, na? These are very much important because we have to apply the proper chlorine dose. Otherwise, if it is in excess, then it will be problem, and if it is less amount, then disinfection will not occur. So, this is very important. Now, I will discuss about the methods now. Okay. An iodometric method for total chlorine residual determination. Total chlorine means chlorine, free chlorine residual and combined chlorine residual. This total is means both combined. Okay. How to determine it? The stepwise it is written, the sample water after adjusting the pH at 3 to 4, at low pH it has to be done. It is this determination is done at low pH. What is the low pH? This is 3 to 4 pH. And how it will be maintained? This is by acetic acid, maintained by acetic acid. Is treated with excess Ki, potassium iodide. So, we have taken some samples, say for example 50 milliliter sample or 100 milliliter sample, whatever, and then we have to adjust the pH by using acetic acid in this range. After that, we will add Ki in excess amount. Then what will happen? When we add Ki, then you see here the reactions from 1 to 5, it is shown. Chlorine reacts to produce the iodine, then HOCl reacts to form the iodine, OCl minus forms iodine, NH2Cl, that is monochloroamine, that is produced, this the combined chlorine residual. So, it is also forming iodine. then dichloroamine, it is also forming iodine. So, all these are all the total chlorine, that is why it is written total chlorine, all are producing iodine. Now, iodine, to determine iodine, the quantitative way it is producing iodine. So, that how can we determine? It is everybody knows, it is the titration with thiosulfate S2O3, sodium thiosulfate Na2S2O3, it has to be titrated. And then when it is titrated, it is the balanced equation is shown. This is the tetrathionate S4O6 2 minus, tetrathionate is formed. Okay. And so, what is the indicator here? It is the starch. Starch is the indicator. So, we all know that for this type of iodometric titration, we start the reaction, we take the thiosulfate solution in the burette, we take the solution where iodine is generated, that we take in the conical flask, and after that we start addition of thiosulfate, and we have to use the starch as the indicator. But when we will add starch, from the beginning or after some time, or when? So, we all know that iodine has the color brown color, or if it is concentration is less, then it is yellow color. Then if it is brown color, then in the beginning we will not add starch. We will start our addition of thiosulfate, then slowly the color will be become less intense. That means, initially if it is brown, then it will slowly become yellow. Then when we see the straw yellow color, that means very faint yellow color, then we will add the starch indicator, and immediately we will see the blue color formation. So, we have not added in the beginning. When lot of iodine is already transformed into iodide, then only little amount of iodine is there showing the straw yellow color, then we will add the starch. Okay. And then immediately it will be dark blue color, and we will then continue the titration with thiosulfate. Within 3, 4, 5 drops, the color will discharge, that blue color, and then that is the end point. Now, the question is, why from the beginning we have not added the starch? Why after almost at the end of the titration we have added this? Okay. So, there are so this is our question, this is our home task. Okay. So, this is a very good question. Even I ask the students in masters level, they cannot answer properly. What is the reason behind this? If we add in the beginning, what will happen? That is the thing. Okay. So, this is the question. We will discuss maybe in the next module. Okay. So, calculation we can see here that 2 moles of thiosulfate is equivalent to 1 mole of iodine. You can see the balanced equation. So, 1 mole of iodine and 1 mole of iodine and which is equivalent to 1 mole of chlorine. Here you see 1 mole of iodine is coming from 1 mole of chlorine. So, this is the it is the beginning of the calculation. After that we can write that 1 mole of thiosulfate is equivalent to 0.5 mole of iodine, 0.5 mole of chlorine. So, 35.5 gram of chlorine. Okay. So, 1 mole of thiosulfate means 1 milliliter 1 molar thiosulfate is equivalent to 35.5 milligram, because 1 mole means here 1 mole thiosulfate means 1000 milliliter 1 molar thiosulfate, but we are taking 1 milliliter. So, here it is becoming milligram, okay, gram to milligram, and then the molecule. Now, the question is coming. So, this is the basis of the calculation. From here you can start. And now, the molecular weight, this is my question, the molecular weight of thiosulfate is m. Say for example, you do not have to calculate. Okay. Say for example, the molecular weight of thiosulfate is m, then what is the equivalent weight? This is my question. So, this is the reaction, it is going on. S2O3, 2 moles of S2O3 is giving S4O6 2 minus plus 2 electron. Okay. This is the reaction that is happening. So, what is the molecular weight of thiosulfate? If the what is the equivalent weight of thiosulfate if the molecular weight is m? This is also home task. Okay. Actually, you see, I am giving the answer. Actually, molecular weight and equivalent weight will be the same. because here you see 2 electrons are involved. So, per 1 electron what is the amount, that is the equivalent weight. So, per 2 electron 2 moles. So, 1 electron 1 mole. So, molecular weight and equivalent weight is the same. But when I give this to the lab viva, then many people, most of the students, they cannot answer properly. They write m by 2, somebody writes m by 4, like this 2m. Okay. So, this is the thing. So, when something is like redox reaction, then you have to think about the electron, how many electrons are involved in transfer. Okay. And when you think about the acid, then you have to think that how many H is present, like H2SO4 molecular weight by 2, HCl molecular weight by 1. Okay. So, because 2 hydrogens are present in H2SO4, so molecular weight by 2 will be the equivalent weight. For HCl it is 1 hydrogen, so it is same. But redox reaction is not like that. And for salt, say for example calcium carbonate, you have seen calcium carbonate, the molecular weight is 100, but equivalent weight is 50. Why? Because 1 calcium is there and the valence of calcium is 2, so it will be divided by 2. Okay. Now, so you understand that the iodometric method can be used in low pH condition, it can be used for total residual chlorine determination. Okay. Now, here it is free chlorine and chloramine determination separately. Sometimes we need to have this method, no, by DPD method. Okay. How it can be done? It is very interesting method. Free, you have to listen carefully. Free chlorine residuals are capable of oxidizing NN-diethyl paraphenylene diamine, abbreviated as DPD, to red colored compound, which is an oxidized product of DPD. So, chlorine, you know, chlorine is an oxidizing agent. So, DPD is a reagent which can be oxidized by chlorine to give a red color. Okay, clear? Now, the pH range should be 6 to 6.5. pH is adjusted by phosphate buffer. You know buffer. So, in my first module I explained. So, pH is maintained by using this. Now, the red colored compound is produced, it is quantitative to the chlorine concentration. So, how much chlorine is there, that much oxidized DPD will be formed. Okay. Now, what you will do? This red colored product can oxidize quantitatively ferrous ammonium sulphate, which is also known as Mohr salt. Ferrous Fe2 plus can go to Fe3 plus, right. So, it is oxidized. So, this red colored product, which is the oxidized product of DPD, can oxidize the ferrous ammonium sulphate, or rather you can tell that ferrous ammonium sulphate can reduce this DPD oxidized product, that is red colored product. Okay. And ferrous ammonium sulphate is a primary standard. So, you can prepare the standard with known concentration of Fe2 plus, and you can titrate the red colored complex that produced in your conical flask, say for example, and then how much Fe2 plus is required, you can see from the titration. Then you can easily calculate how much actually chlorine was there to oxidize the DPD. So, it is very nice. So, first to sample water, an excess amount of DPD is added. So, how much DPD should be added excess, but it will be quantitatively oxidized, right. How much chlorine is there, according to that it will be oxidized, even if you, and that actually reagent has to be added in excess. Then the solution is titrated with standard ferrous ammonium sulphate solution. At the end point, sharp color change from red to colorless is observed. Okay. This gives a measure of free chlorine. This is a free chlorine, because free chlorine, only free chlorine here and at this condition can oxidize DPD to some red colored compound. So, this is written in a simple way: sample water, pH adjusted to 6 to 6.5, excess DPD added, red colored solution, then titrated with standard Fe2 plus solution, colorless endpoint. So, that is the path. And the calculation is like this: chlorine, you have chlorine, free chlorine. So, chlorine it is acting as oxidizing agent. So, it is reduced, and then Fe2 plus is oxidized when it is oxidizing the when it is reducing that DPD oxidized product. So, this is the calculation. Now, free chlorine and chloramine determination separately. Okay. The solution after the free chlorine determination is treated with excess Ki. Free chlorine you have already determined. Now, you want to determine the chloramine concentration. So, how will you do it? Okay. It is a mixture. Say for example, free chlorine is also there, chloramine is also there. So, free chlorine you have already determined. Now, you want to do the combined chlorine, okay, chloramine, combined chlorine. So, how will you do it? So, that is written here step by step. So, what you will do, the solution after the free chlorine determination by DPD method, it is treated with excess Ki, then you add Ki there, okay, excess Ki. What will happen? Then so liberated iodine by chloramine. You have seen in the previous slide that iodine is generated by chloramine, okay, iodine is generated from Ki quantitatively. So, iodine will be liberated. That liberated iodine can again oxidize DPD. So, liberated iodine will oxidize, chloramine will not oxidize, liberated iodine will oxidize the DPD, okay, to red colored product. Same reaction, but it is done by iodine. And how iodine is produced? Iodine is produced from chloramines after reaction with Ki, okay. So, then so red color is produced, then again you are tightening with more salt, the end product will be colorless, same way like the previous one. So, it will give the measure of chloramines, okay. Now, if there is monochloramine and dichloramine both, then how you can determine? It is giving total chloramine, but if you want to do the estimation of monochloramine and dichloramine separately, then what you will do? Again kinetics is coming. What is there? Thus, if a small amount of Ki is added and the product produced red color is titrated with Fe2 plus immediately, then it gives a measure of monochloramine. Why? I will tell you. This is kinetics. Monochloramine and dichloramine, they react, the kinetics is different, okay. Now, after the measurement of monochloramine, again add excess Ki, then iodine is liberated slowly. The liberated iodine produces the red color by oxidizing DPD. Same method, but here slowly produced, it is by dichloramine. Quickly produced monochloramine, you have already determined monochloramine, then again Ki added, you are allowing some time, then dichloramine will produce the oxidized DPD. Then you are doing the same reaction with the iron 2 plus, okay, and then you are determining the dichloramine. So, it is basically kinetics, depending on the kinetics you are measuring monochloramine and dichloramine separately. The liberated iodine produces red color by oxidizing DPD. This red color oxidized DPD is titrated with iron 2 plus, it is same, but this time it is dichloramine you are getting, okay. So, same method you are using to determine DPD is the reagent you are using to determine free chlorine first, it is direct, no Ki is added, then you are finished. Then there dichloramine and monochloramine is not coming into picture. Now, you are adding Ki, okay. Then if you add Ki, excess Ki, then both chloramines together will come, but if you add small amount of Ki and immediately you titrate, then you will get the monochloramine. DPD is there, forget about DPD now, DPD is there everywhere, okay. And now, if you do excess amount Ki and allow some time to keep, then dichloramine is coming. So, it is a very interesting method. Free chlorine and chloramine determination separately, the same thing, it is written in a nutshell. Chloramines, mono and dichloramine, excess Ki and excess DPD added, red colored product titrated with standard Fe2 plus colorless endpoint. It is the combined, okay. Excess, so both are reacting, okay. Excess you have added, both are reacting. it has been observed that oxygen also oxidizes DPD slowly. Oxygen is also an oxidizing agent, right. So, it can oxidize DPD also. This reaction becomes faster in presence of metal ions. Again, if metal ion is there, it catalyzes. So, how to resist it? How to make the reaction of oxygen with DPD slower? By adding EDTA, because all the EDTA very good complexing agent, it can complex with metal ions. So, if you can complex this metal ions with EDTA, then it is no more a catalyst, it cannot act as a catalyst. So, this reaction will be slowed down. So, oxygen will not hamper, because titration in nitrogen atmosphere or some other inert atmosphere is not possible. Okay, oxygen you have to allow, okay, but you can do this way, then minimized, error is minimized. How to overcome this problem? I am not written the answer, but I told the answer. So, the whole method is based on different kinetics of DPD oxidation. DPD oxidation by free chlorine fast, DPD oxidation by chloramine slow, DPD oxidation by iodine fast. Oxidation of iodine by monochloramine is faster than that of dichloramine. So, you have used all these things in this measurement. Okay. Other methods are also there. Orthotoluidine method, this is a old method, colorimetric or spectrophotometric. Which is colorimetric? You can extend it to spectrophotometric also by doing the calibration curve by using the spectrophotometer. Okay. But colorimetric is just color you produce and color you compare, different colors you produce with different concentration, then you compare with your solution, with your sample solution after formation of color, that is the colorimetric. Spectrophotometer means you have to standard curve you have to prepare, and then with the sample also you have to develop the color and then measure the absorbance value and put it in the calibration curve, then get the concentration. It is a finer method and more accurate. Okay, so how can you do colorimetric method? Orthotoluidine, not toluidine, toluidine is something else, toluidine. Orthotoluidine was used as a colorimetric indicator for chlorine residual. You see the year 1909, so Phelps, very old method. Free chlorine can oxidize orthotoluidine to form a haloquinone. Quinone I told that sometimes it has color, having yellow color in acidic media. Okay, free chlorine can do this. Color standards, this is done by this color standard. Why these are important? You know, that time spectrophotometer, all those things were not there. So, simple methods are used, but because chlorination has started already. So, how to determine the how much chlorine you will use, how much chlorine is there, residual chlorine. So, this is color standards. So, some standards you can prepare, say for example, with known concentration of chlorine you add the reagents and some color is developed, then you seal it, then this is the standard. So, your sample you do the same thing and compare the color. So, comparison with standard color. Sometimes disc also, we have used this fluoroscope, some disc, okay, disc has colored disc, you put it there, your prepared solution, it is giving some color. So, you match with the discs and then you will know what is the concentration. These are very useful for field test, because in the field you cannot carry the instrument, only the test kit is very good to carry, small kit, you just go there, you mix it there on the spot and then you compare it with the disc or with the standards, it is easy. But can be estimated spectrophotometrically also to have quantitative measurement of chlorine concentration. Same method, but you can extend it towards the spectrophotometry. But it has low accuracy. Orthotoluidine method is not very accurate method. You can use it, sometimes that much accuracy is not needed also. So, but you can use it, but it is not very accurate method. But one thing is important, orthotoluidine is known to be a toxic substance. Now it is known. Now we know that now we are very much concerned about our health, na? And also green chemistry approach. I told you the green chemistry approach in catalysis. So, toxic substances we do not want to use because ultimately it will go to the environment and we do not want that, and it has the carcinogenic potential, it is cancer carcinogenic compound. So, if it is carcinogenic, then again we have to be more cautious, right, and that is why it is not used anymore in the standard method. You know, standard method, there is a book where all the standard methods are there for determining so many things, very huge book, big book. But you know that if you say, for example, you develop some method which you think that it can be a standard method, worldwide it will be used, then it takes so much time. You have to first apply that you want it to be standard method, then it will be verified by so many labs and so many times and by different people and like this. So, it takes 5 years, 7 years time to actually to say that okay, this method is very good. And now again the toxicity of the reagent and reproducibility, everything is there. So, it is no more used in the standard method because it is toxic, it is not that accurate also, but it is a very old method, it has the history. You see the year 1909, okay. And also field application also, field test also, as a kit it was used for a long time. Now, there are some questions in this module 5, I picked up some questions. How to determine the amount of bleaching powder required to disinfect a water sample? How much bleaching powder you will use? How to know? Break point chlorination curve you have to draw. You have to do some experiments. You have to vary the dose in different containers. You take the water, same volume water, you add the different doses of chlorine, keep it for some time, then measure the residual chlorine, and then you prepare the graph, then you will know how much is the demand, then you apply that type of chlorine dose to be in the safe side. Okay. What is the demand? Chlorine demand, chlorine applied minus residual chlorine. Then there are so many compounds you have seen, chlorine, this 0 state, then chloride, then HOCl, OCl minus, ClO3 minus, ClO2 minus, ClO2 gas. So, what are the names and what is the oxidation state of chlorine there? Though this is very interesting. And explain why addition of chlorine tends to decrease the pH of water and hypochlorous increases the pH, that I already answered. What is the relative significance of free chlorine residual and chloramine residual in water disinfection practice? I told you during transport the residual combined chlorine residual is very important, isn't it? That is chloramine residual, and free chlorine residual, although it is better disinfectant, but it is dissipated fast. Now, references, same book, Sor McCarthy and A.K. Das, that is environmental chemistry with green chemistry. All the methods they are written very nicely. In standard methods also you can consider, there is a very good standard method book, water and wastewater analysis. So, there also all the methods you can consult, but here in these books also it is nicely written, you can read it thoroughly. If you want to do the experiments, if you want to measure the things, chlorines or nitrogen containing compounds like nitrites, ammonia, nitrates, then you can read these books to have thorough knowledge. And as a conclusion, I can tell from this lecture, in the disinfection practice, it is important to determine the total chlorine residual. The determination method is described. The methods to determine the free chlorine and combined chlorine separately are also described. There are different methods, you can choose which one you will apply. Thank you.